Hello, now we have discussion about divergence first, then later we'll see the divergence theorem. So first we need to understand what is the divergence. Okay. So divergence of A at any given point is what? It is the outward flux per unit volume. So what is the flux? Flux is the number of fields crossing through the particular volume. Okay. So that's why here we are talking about the per unit volumes. So when we'll talk about the flux, or later we'll have a discussion about the flux density also. So that flux density we are going to calculate for the per unit area. So here number of fields passing through the volume is called as the flux. So we'll concentrate here on outward flux per unit volume. Another consideration is that when volume shrinks about P. So at particular point P, when volume is going to shrink, slowly it is going to decrease. It is not zero, but it is going to decrease. That is called as the divergence. So now suppose, for example, if we'll consider another situation, if that field is going to be, suppose this is the point P here, and direction of the field is like this. So it is moving outwards from this point P. So this moving outwards flux we call as the positive divergence. So here we have positive divergence. Which type of the divergence? Positive. Since it is moving outwards. Whereas in case of another situation, suppose this is the point P, okay, and direction of line of force is like this. All are converging towards the point P, okay, from all sided. So this is called as the negative divergence. Now suppose we'll consider the another situation in which this point P is here and lines of force that fields are passing like this without any deviation. There is no any change in this, okay? It is going to pass from one side to another side. So this will be called as the zero divergence, okay? So here we have seen positive, negative and zero divergence. Now here what is important thing that how we are going to define the divergence with the help of expression. Again, we'll see the divergence in three different coordinates. Okay. So now since volume is going to shrink, so finally divergence is given as divergence of A. Okay, A is any vector. For that, what can be the divergence? So in this case, this divergence is represented like this. We can write also del dot A. And condition is that what here? This volume is going to tends to 0. So finally, here we have to consider the surface integral of this A over the closed surface. So when surface is closed, then only is going to form the volume. Okay. And this is divided by del V. So this is the definition of the divergence. Now in three different coordinates, we have to see that what is the expression of the divergence. So first we'll have discussion about the Cartesian coordinates. So in the Cartesian coordinates, what are the variables we have? What are the parameters we are going to consider in the Cartesian coordinates? That is the important here. So you know that in the Cartesian coordinates, what we have? X, Y, and Z is there. So finally, earlier we have discussion about the gradient also. Okay, so there should not be confusion about this. So this now divergence of A in Cartesian coordinates. So this vector A will have components. What are the components we'll get here? Ax, that will be in the unit. This Ax is the unit vector. Ay, capital Ay, and a small ay is the unit vector. Again, we have Az and a small az. A small az is the unit vector. So finally, we are going to write the gradient of A. In that case, if you see that the dot operator will not come, okay? But here we are going to use the del dot A in case of divergence. So this divergence will be given here dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z. So these are the three components in the Cartesian coordinates. Similarly, we'll have in cylindrical coordinates. So in case of cylindrical coordinates, what are the variables or what are the parameters we are using here? What are the parameters? Can you recall? So we have here rho, phi, and z. Okay, where rho having range 0 to infinity, phi is 0 to 2 pi, z is the minus infinity to plus infinity. So again, if you'll see that in cylindrical coordinates, if you are going to consider any dimensions, okay, so for that, what are the sides, what are the edges there, so that we are going to represent in the form of like we have that is the differential part elementary volume, how we are going to calculate. So for that, what are the sides of that cube or cuboid, what we are going to consider. So that we are writing as in the form of d rho. Again, we have another expression is what? Rho d phi. Then we have dz. These are the three edges of the cuboid. So for that now, how we'll write again divergence. Okay. So here A will have component A rho, A phi, A z. Okay. So similarly here if you see that how you are writing dou by dou rho. Okay. And first component of A is what here? A rho. Now one small change here, it is multiplied and divided by the rho. Okay. So that it will be balanced. Finally, second component we have here dou A phi. A phi component of A, and already we have rho d phi. So similar thing is going to come here, rho d phi. Third one is dou Az by dou z. Okay. So this one here we are going to get the scalar quantity. So divergence of any vector, we are going to get here a scalar quantity. That's why direction is not shown here. Okay. Next, after cylindrical coordinates, next coordinate is what? Third one is which coordinate? A spherical coordinate. So in case of a spherical coordinates, what are the variables we have? R, theta, and phi. And you are aware of the range of r, theta, and phi. So that is going to change from r is going to change from the 0 to infinity, theta is 0 to pi, and phi is 0 to 2 pi. So there again we have seen that if you are going to consider elementary volume in the spherical coordinates, so that sides of the cuboid, that is we have dr, then we have r d theta, and you have r sine theta d phi. So same thing we are going to use this concept here. So divergence of vector A in the spherical coordinates. So A will have components AR, A theta, A phi. Okay, so those things we are going to consider here. Now finally, so how we'll write here? Dou by in general, dou by dou r, and AR component of the vector A. Now it is multiplied and divided by r square. Okay. Plus, now again, here in general, if you write, how will write? Dou by r dou theta. Okay. And this which component is going to come here? For A theta component is going to come. Now it is multiplied and divided by sine theta. So that's why here again we are writing the sine theta. Last one we have, in general, how we'll write? Dou by A phi by r sine theta dou phi. Okay. So like this we are able to write the divergence of any vector A in three different coordinates, and that is going to give us the scalar of that one. Okay. And next we have divergence theorem. That is also very important. So divergence theorem states that outward flux. So here outward flux always we are considering as the positive. That's why outward flux of a vector field A through a closed surface. Okay, surface is closed, is same as the volume integral of the divergence of vector A. So here we have relation between the surface integral and the volume integral. So that surface integral of vector A over the closed surface. That's why putting the circle here on the integration. Over the closed surface is what? It is equal to the volume integral. So we'll use here V. So that is the triple integration here. Volume integral of the divergence of the vector. So del dot det is the divergence of the vector, and dV we need to write here. So this is the divergence theorem that is going to help us to simplify the many solutions. Okay, so we need to keep in mind what are the parameters. Thank you.